In our last video, we saw that derivatives are essentially a measurement of the rate of change of a function, which means that when you have a linear function, they're quite straightforward to evaluate because it's simply the slope of the linear function. But when we're dealing with a nonlinear function, and in the graph here, we have this nonlinear function in blue that has this curve to it, which means that it's not going to have a constant slope. The slope is going to change. Well, one way for us to think about derivatives for such a function is to consider a tangent slope. And what a tangent slope essentially is a tangent slope corresponds to 2 points. Let's say that this point right here is something like 1.00001, something like that. When we look at the function at two values of x that are very, very close, such as 1 and 1.001, we can determine what the corresponding y points are. And using those two y points, we can actually figure out what the slope of a line that runs through both of those points would be. And that's our tangent slope. It's really important for us to think about these tangent slopes at unique points because it really can vary. As you see here with our function in blue, at the beginning, the slope is quite high for the tangent line. But as we move further along, the slope will become less and less steep. And we would imagine that if we continue drawing this line out, it's probably going to level out to the point where the slope is relatively flat. Now, algebraically, we can actually determine the tangent slope using some skills that you probably had to develop at some point in your algebra class way back in high school. You might remember something called point-slope form, which tells us that the difference between y2 and y1 is equal to the slope of a line multiplied by the difference between x2 and x1. Now, if we rearrange that equation, what we'll actually find is the expression for the derivative. We could say that y2 minus y1, and then moving the x2 minus x1 into the denominator here, like that, like so, x2 minus x1, oops, that should be a 1, is equal to m. But again, what we're seeing here is exactly equivalent to that expression dy dx that we saw before. In that sense, when you're thinking about dy dx for a nonlinear function, think about it in terms of the slope of the tangent line, which we draw by those 2 points that are very, very close to each other in the function. So in this example, I define 2 points that are quite close. x1 is 3 and x2 is 3.00001. And we want to see what the tangent slope would be for the function above, y is equal to x squared. Well, if we feed this function the number 3 for x, we get y1 is equal to 9. 3 squared is 9. y2 is actually going to be equal to 9.0000036. Alrighty. Now we have 2 points. We have x1, y1, which is 3, 9, and we have x2, y2, which is 3.00001 and 9.00006. Now, if we want to plug all these values into our expression to find the slope, we'll end up with y2 minus y1, which is 0.00006 over x2 minus x1, which will be equal to 0.00001. So you might remember these will cancel out. So this is, it's essentially 6 over 1, which we know is equal to 6. Illustrate this on using the current graph. So by using that 3.00001, which is really close to 3, and corresponds with a point that's really close to 9, which is 9.00006. By using those 2 points on our function, y is equal to x squared, we can find the slope of the line that is tangent to the point 3. In other words, if you took those 2 points that are so close, they're essentially the same point right here. They're essentially this point. They're so close. If you draw a line connecting them, that line will have the slope of 6. And as we showed before, this slope is equal to dy. Apologies for that. I'm a lefty, and I drag a little bit with my left hand, which makes writing a little challenging on a tablet. Any lefties out there will sympathize. We've already discussed in the previous video that this slope is equal to the derivative evaluated at that particular point. Oops. Now, the example that we just showed gave us an idea of how we could actually use algebra to find the derivative for a given point in any sort of function, a linear function or a nonlinear function. But this is not always enough for the analyses that we like to do. Instead, we often want to find f prime x, which is a function that describes the full set of derivatives for fx. In other words, it often isn't enough for us to know what the rate of change is for a given x, but we want to know we want to get a function that tells us what the rate of change is for any x given a function fx. And we'll cover this, and there's a little typo, we'll cover this in the next part of our series.